Okay, so we'll be talking about, so one way, as I said, can be to restrict the input. And the other, so yes, on certain instances, so what we said that we have to deal with NP-complete problems in real world sometimes, and we can't just say that, okay, they are not polynomial time solvable, so we just don't care about them. We still need to solve them. And so one way of solving them in some instances can be to restrict the input. On certain instances, they can be easy. That's easy. Or another way is to not look for compromises with exactness of the solution. Get approximate solutions, but in polynomial time. So this, we will see some of it tomorrow. And some of this we'll see today. Restricting the input, right? So one of the problems that we have seen is, which is NP-complete, is vertex cover. Right? Given G is equal to V comma E, does there exist S subset of V of size at most K such that for all UV in E, either, or let's say UV intersection S is not equal to empty. Right? Either U is in S or V is in S, or both. Right? So this is the problem that we want to solve, but we know that this problem is NP-complete. So what is, how much time does a naive algorithm take? For vertex cover. Any ideas?
N into 2 to the power n.
N into 2 to the power?
And for every subset, we will check if it works or not.
Good, but then we don't need to go for every subset, right? We can only go till subsets of size k because
yeah, okay, yeah.
Right. So what we can do is n choose k, and then maybe n square, right? For checking, let's say n square is a bad bound, but let's say n square. Okay.
Yes, sir. Yes.
Okay. So what is this? This is how much? This is order of n choose k plus 2, right? Because this is n to the k, and this is like quite bad. So suppose n was 1000 and k was just 10 also, suppose. Then how much time do we spend? We spend like, let's say 1000 to the 10 also, which is like 10 to the power 30. And if like a machine does 1 million operations per second, then this will take 10 to the power 24 seconds, which is huge. Like this is more than the age of universe, like multiple times, like order of magnitude times different, right? So this is not really practical to have this kind of running time, okay? But what if we can get a running time of the sort, let's say 2 to the k, n square? Then this is much, if like, for example, so suppose the point here is that we are looking for a small vertex cover as compared to the size of the graph. So if we have the small vertex cover, if k is 10 again, then this becomes 2 to the 10 and 1000 square, which is not much, right? This is very feasible. Right? So this actually is like, this is an area which I work in extensively. It's called parameterized complexity, where actually this K also becomes a parameter. And then we measure the running time in terms of both things, in terms of K and N, and how the interplay happens and how we get better and better running times when we restrict the parameter to be a certain value. Okay. So we'll see this algorithm today, and as you can see, this is much more desirable than this algorithm. So we want a 2 to the k n square algorithm, right? And how does the algorithm work? And the idea is very simple. Pick an edge, one of u and v must be in a solution in any vertex code. So basically, we can do a branching algorithm, branch on the possibilities. And the main thing is that in both the branches, the budget, which is k, decreases by 1. So branching meaning we do solve it recursively. So suppose we have this instance of g comma k. What we do, we pick an edge uv, and then in one side we delete u from the graph because all the edges which are incident on u have been covered, and we decrease the budget by 1. And in the other branch, we do this, right? So the instance is of the form g comma k, right, in vertex cover. So from g comma k, what we do, we go to two instances. In one we delete u, and in one we delete v, right? And then we solve it recursively. So what does it mean? So let's write it down as an algorithm, and then we continue this process. Right? So let's write down the algorithm. Vertex cover, let's say, takes g comma k, right? And what does it do? So first thing is like some base cases we need to tackle with, that if G has no edges and K is greater than or equal to 0, say yes, right? Second is if G has some edges and K has become 0, then we say no. This is the base case. These are the base cases. Now, otherwise G has some edges and K is not 0, right? K is greater than 0. So now pick, so this is the else part, but fine, just pick UV in E, right? And solve G minus U, comma K minus 1, and G minus V, comma K minus 1. Right. And fifth is say yes if any of, so this is recursively. Say yes if any of the above say yes, and say no otherwise. And that's it, right? So this is the algorithm. And so let's do a quick correctness. So G comma K is yes if and only if one of G minus U comma K minus 1 or one of these, right? So one of this and G minus V comma K minus 1 is yes, right? So this will prove the correctness of the algorithm, right? The base case, of course, you can see that, that is correct. That if K is 0, then you cannot cover any edges. If there are no edges to cover, then you can say yes. Okay, and what is the proof? The proof is very simple. If G comma K is yes, then one of U and V has to be part of any vertex cover. So that means G, so let that vertex cover S be a vertex cover of size K, since G comma K is a yes instance, then S minus U and S minus V are vertex covers of size K minus 1 for G minus U and G minus V respectively. So they are yes instances. They are both yes instances. In fact, so we wanted to show that one of them is a yes instance, but actually both of them will be yes instances if G has a vertex cover of size K, right? But for the backward direction, so this is the forward direction. Now suppose G minus U comma K minus 1 is a yes instance. Let S be a vertex cover of size K minus 1 for G minus U. So now you have this G minus U, and here is U that you have deleted to get G minus U. So all the edges here are covered by some vertex cover. So this is the vertex cover S. And what edges are not covered? The only edges that are not covered can be this, and then you include U in the solution. So S union U covers all the edges in G. So G has a vertex cover of size K. So G comma K is a yes instance. And similarly, you can show for the other guy also, for V. And this shows the correctness, that you just need to branch into these two things. And then you are, if one of them say yes, then you say yes, otherwise you say no. So this is fine. But the main thing we wanted was the running time, right? So let's do the running time analysis according to the picture that we have. So we had G comma K, then we had G minus U comma K minus 1. From there we got, so let's call it some G. Okay, let's call it G minus U only. Then we have G minus V comma K minus 1. Then from here we'll get something comma K minus 2 because we'll pick another edge. We'll pick K minus 2. Again here something comma K minus 2. Something comma K minus 2. Right? Because we are solving it recursively. Right? And where will this stop? How many levels can this tree have?
Sir, K.
K, right? K levels.
Sir, should be minimum of n and k.
No, because we are decreasing k, right? In every level, we are decreasing k. K is always less than n. You can anyway say no if k is more than n. Anyway, you can say yes if k is more than n because there exists a vertex cover of all the vertices. So we can assume that k is less than or equal to n. If k is greater than n, say yes. You can say that like initially somewhere. That is a trivial case. Okay. So always assume k to be smaller than n. Yeah. So this is k level. So how many nodes can be there in this graph? In this tree?
2 to the power k plus 1.
2 to the power k plus 1 nodes. Right. And at each node, how much time we are taking? We are just picking an edge, right? We are performing this and we are just picking an edge. We are not doing anything more and we are calling the things recursively. So actually, at each node, at most n square time, let's say. So total time is order of 2 to the k n square as we wanted. Right. So this is a branching algorithm which deals with this problem and gives a very nice algorithm which has a much better running time than the naive algorithm that we had, which is order k to the n to the k plus 2. Right. Any question about this algorithm? So what will happen at so what is happening actually is that now if in any of the branches if you say yes, then you'll say yes originally, because you'll say yes here, say yes here, say yes here, say yes here, and finally say yes here. And you'll say no if all the branches say no, basically.
Time at every node.
Yeah? Yes, Mrityunjay, say again.
Why do we need n square time at every node?
I mean, we might be able to do it in linear time, but let's just find a bad bound. In the end, maybe.
Don't we just pick an arbitrary edge at every node?
Yeah, we can pick an arbitrary edge at every node, but but still you have
removing u and v to create new graphs will take time, right? Order
exactly.
time.
Yeah. So that is what I mean. Let's just take it might be done in order n time, but let's just take a worst bound to be n square. The idea is this function that needs to be converted. Yeah, deleting edges can take linear time.
Sir, also won't the computation in the leaves take some time because we need to check there is no edge in the leaf graph?
Exactly. It does. That's what I'm saying. That but checking no edge actually can be done in linear time also, right? So fine. I mean, maybe it can be done in linear time, and I'm sure it can be done in linear time. I mean, linear in n, or linear in m, okay, or n also. In fact, there is an algorithm which can do this in 2 to the power k plus n square time also. But I mean, I'm not going there. How to do that? And in fact, this 2 can be decreased to 1 point something 237 to the k also by doing some. So this is a very simple kind of branching, but what if you select an edge in a nice way or a vertex in a nice way to delete and so on? So if you do a lot of effort, then it can be brought down even more. So I think this is the best running time right now. I might be wrong. Okay. So this is one way to deal with that. Okay, you have a parameter and you are only looking for problems which have small vertex cover where k is small, and for that you can solve this. So this is the problems which have these kind of algorithms are called fixed parameter tractable, and these algorithms are also called fixed parameter tractable algorithms. So this is called FPT. So the problems are also called FPT and the algorithms are also called FPT. So this is the class of problems which admits algorithm of the form f of k, polynomial in n, where k is some parameter. So when the parameter is small, then this becomes efficient. And the thing is that this f is bound to be exponential for NP complete problems, right? Because otherwise, if this is polynomial, this f is polynomial, then the whole function will be polynomial, which is not possible for NP complete problems. So what we are doing essentially is taking out the exponential from n and putting it only in k. And since k is small, this still remains, feasible. The running time remains feasible or efficient. So this is the idea behind this whole field of algorithms, which are called fixed parameter tractable algorithms, which I work in. So if I offer a course like maybe next semester or next to next semester, I would if you guys are interested, you are most welcome to take that course. Or if this idea interests you, you can ask me for pointers, and then I can give you some. Anyway, so this is something in which we can deal with the NP complete problems. And another way is to restrict the graph or restrict the input instance. To be just restrict the input instance, right? Like for example, did we see an algorithm for vertex cover on bipartite graph? I think we didn't, right?
That was by matching.
Yeah, matching, right? We saw the matching. But in bipartite graphs, there is this theorem which says that maximum matching, size of the maximum matching is equal to size of the minimum vertex cover. Right? And we saw how to compute. So this is called Koenig's theorem. And so we saw how to compute the maximum matching in bipartite graphs. So we can solve minimum vertex cover in bipartite graphs in polynomial time. Right? So what about some other graphs? So that means this is a problem that is NP complete, but we can solve it on bipartite graphs in polynomial time. So similarly, if we can restrict the graph class, if we don't don't want to solve the problem in the most general way, which is on general graphs, then we can gain something by doing this, that we restrict the input class and then we can get the solution in polynomial time. So one very natural thing on which things might be simpler are trees. So many problems become polynomial time solvable on trees. Okay. So let's take the independent set problem, for example. So we have seen independent set. So input is g comma k. Question is, does there exist? I'm not going to define independent set right now. S subset of V mod S is greater than or equal to K. It is a maximization problem such that S is an independent set. Okay. Now this problem we know is NP complete. We have seen that. But what about trees? Right? And it turns out that actually a greedy algorithm works. And what is the idea? That, okay, you have a tree and you have a leaf, right? So suppose you want to include this leaf or its neighbor, suppose you want to include this. Which vertices get blocked by it? So call it V, call it U. So U gets blocked, right? It cannot now be in the independent set. But if we include U, then more things get blocked. So idea is to include the leaves. Greedily, right? But then if you include this leaf, maybe something is like this. If you include this leaf, then this cannot be, so you need to delete it. It's not that you delete just this guy and now it has become the leaf, so you can include it. So you need to delete all their neighbors. Right? But the lemma is actually very simple, which shows this. And what does the lemma say? Lemma says that if T is equal to V comma E is a tree and V is a leaf, in T, right? Then there exists a maximum independent set including V. Maximum sized independent set including V. That contains V, right? And what can be the proof of this? So let V be a leaf and let UV be the only edge incident on it. Okay. So let's say that, let's start with let S be a maximum sized independent set. Of G or of T. Okay. So how can we now show that there exists a maximum size independent set of the graph including V of the tree?
That S must have U because it is maximum.
So S must have either U or V, right? If S,
Yes, if V is not present then.
yeah, if S has V, then we are done, right? Now, if S, so else, that is S does not have V, then S must have U because S is maximum. Because if it does not have both, then you can include like increase the size of S. Why? Because then S union V you can put. This becomes a bigger independent set, not possible. Contradiction. So then S must have U. And what is the claim? Claim is that S minus U union V is an independent set in T. And why is this the case? So call it S prime. Because S minus U is already an independent set. And V does not have any edges. To in fact V minus U, right? So S prime is an independent set. And size of S prime is equal to size of S. So there exists an independent set, a maximum size independent set. Containing U. Right? So this can now easily be turned into an algorithm. And what will the algorithm do? I am not going to describe it in detail, but pick leaves one by one, delete their neighbors. Any question about this algorithm? And this can be done in easily polynomial time, right? You don't need to like do something very fancy, or you don't need to guess anything or go through subsets or anything. You just have to find a leaf, delete it, include it in your independent set, delete its neighbors, only one neighbor actually because it is a leaf, then recursively find the independent set in the remaining graph. The fine point is that the graph might not remain connected after this, after deleting its neighbor, but that's fine. You can just generalize this for forests. So on. Still, you can just pick the leaves.
So shouldn't it be isolated vertices as well with leaves, because like this is said that
Yes, that's correct. Leaf is degree less than or equal to 1.
Okay.
Any other question? In fact, there is another problem that can be solved on trees, for example, which is maximum weight independent set. So your input is G, K, a weight function from vertices to, let's say, positive reals. And question is, fine. Question is, does there exist an S subset of V such that summation of weight of V belonging to S is less than or equal to K? So this is the problem, right? That instead of now getting the now you don't count each vertex as one. Now you are given a weight function, right? And now the greedy will fail. Why the greedy fails? Any example or any idea?
So the neighbor of the leaf could have a very high weight.
Exactly. So what you can do is this. Actually, can have very low weight. This is a maximization problem. Thank you for saying it the other way so that. So suppose the leaf has it could have very high weight. You're right. And we want to maximize it. So suppose this had like 1, this has 50, and this had 1, and now you pick the leaf, then you get only 1, while you can get an independent set of weight 50, right? So greedy fails. But now what we can do DP. Okay, and what are going to be the subproblems now for the DP? So we know that we want to get subproblems, and we want to solve those subproblems, and one of those subproblems will be the whole instance and so on. So you have this tree. So I have drawn a binary tree, but it doesn't necessarily have to be binary. Okay, let's make it not binary. Good. So we define. So first we root the tree. At some arbitrary vertex. Call it R. So this is the root. Okay. And let's say T subscript R or T subscript V is the subtree rooted at V. Right. So for example, if this is our V, then this is TV. Right? So what is going to be the subproblems? Maximum weight, independent set of TV for every V. Right? But if you see, even if we compute this, that the maximum weight independent set for TV for every V. So suppose this one contains V, suppose this is V prime. This one does not contain V prime. Then we don't know, like, maybe there was another independent set which does not include V, but now we can include R because of that. Right? So suppose this maximum weight independent set, including V, had weight whatever 100, right? While the one which does not include V 100, which includes V. And suppose 99 does not include V. Right? And suppose R has some weight, like again 100, right? But since you are only storing the one which contains V, then you cannot combine now R to get, 199. So, and plus whatever is here, right? So the thing is that you should also care whether V is there in the independent set or it's not there. So let's say 5 is maximum at V prime. Suppose it does not include V prime. This V prime, right? And then what is the optimum? Let's say, optimum is at least greater than or equal to 204, right? But what you will get, you will not be able to include this R now because you only have the maximum here. So you will not be able to do it. So what you will get is just this 100 and this 5. So we get 105. So this is not a good strategy. Maybe we want to keep both things. That for each TV, we want to keep two independent sets. Okay. And what are the two independent sets? Let's call it opt in V for TV. So max weight independent set of TV containing V, and opt out V is equal to max weight independent set of TV not containing V. And now we can, if we have both these, then we can write a recursive formula. So now what is going to be opt-in of V, given that we have computed everything from below? So we start from the leaves and we compute up, right? And for the leaves, it's going to be easy. I'm not going to write base case. So what is opt-in of V? Opt-in of V is going to be weight of V plus, now you sum. So you have this V. Okay, let me draw another figure here. And you want to compute weight of an independent set that includes this V. So here you cannot have these guys in the independent set. So you sum the out ones, right? U such that U is a child of. Right? And what is opt out of V? So now we don't have weight of V, of course. And now what we do, now we take the maximum of all these trees and they can be combined. So they can be like, they can include the child or they might not include the child. So again, you belong to children of V. Max of opt in of U, opt out of U. So this is what we have the recursion, and like we always do in DP, we can define the arrays, whatever M out of U, which will, right, and M in of U. So this will store opt out, right, of V for all, and this array will store opt in of V for all, right, for all. And finally, compare max of opt in of R, which is the root, and opt out of R, because the maximum independent set might include the root, might not include the root, with K, and answer accordingly. If the max is greater than K, then say yes. If it is not, if at least yes, then say yes. If it is less than K, then say no, right? And so this is the then obvious algorithm which comes, right? That root the tree at node R. This is what we said. For all the nodes U of T in post order, if U is a leaf, then set the values. So for the leaf, this is going to be the case, because if what is the maximum independent set that contains, that is just the leaf itself. And what is the maximum independent set that does not contain in that subtree? What is the subtree? The subtree is the leaf itself. So that has weight 0, and the one that contains has weight U, WU, right? And then otherwise you just set the values. So for leaves, so this is the start of the recursion, start of the DP, like base case. And then for now you have got it for leaves, for all the leaves, and now you can do it for their parents, right? So else set the values like this, and this can be finally return max of. So this actually returns the maximum weight independent set. But what you can do is that if, so let's say that this is equal to some K star, then you can do that. If K star is greater than or equal to K, say yes. Otherwise, say no. Like if we want to make it a decision problem, right? And that's it. So even this maximum weight independent set can be solved on trees in polynomial time using DP. And in fact, it can be solved on some generalization of trees using DP. So this is polynomial time. You can like do a running time analysis. So it can even be solved in polynomial time on a generalization of trees, which is called bounded tree width graphs. And that also, again, that is a big area in research, that what problems can be solved on, these bounded tree width graphs in polynomial time, and so on and so forth. So this is one way of restricting the input. So first we saw that if there is a parameter, and if the parameter is small, how to solve the problem then efficiently. And otherwise we saw that if we restrict the graph class to be trees, for example, or bipartite graphs, then how an NP-complete problem can be solved in polynomial. Right. So any questions about these three algorithms that we saw today? The first one was for vertex cover on general graphs, running in time 2 to the k polynomial in n. The second one was for maximum weight for maximum independent set on trees, unweighted, where we could do greedy. And the final one was maximum weight independent set on trees, where we had to do a DP. Any questions? Okay, so if not, we'll tomorrow we'll see, like, maybe one, or let's see if two approximation algorithms, and that will finish the course. Okay. Thank you for coming. See you tomorrow.